Hello everybody, Adam Lusek here, and today we're going to be talking about quantization. You've probably seen, if you've looked at some large models like this 3.1 Nemotron model from NVIDIA, that it comes out to about 70.6 billion parameters. And the files for this take up a lot of space. You can see that we've got about 30 safe tensors files, and each one of these is about 5 gigabytes. But when we go back to the model card page, we can see that there are quantizations of this. And digging into this, we might be able to see something like Unsloth's version, which is the bits and bytes 4-bit. And we see now that it's 37.4 billion parameters, and in here, there's only 8 safe tensors files, and each one of these are about 5 gigabytes themselves too. So some transformation has happened here between this base model and then the model that we're just taking a look at, and that transformation is what we call quantization, which the broad definition is essentially mapping some sort of input values from a large set to output values in a countable or smaller set. In the context of things like deep learning and machine learning, quantization is more this technique to actually reduce the computational memory costs of running inference on these models by representing the actual internal weights and activations with a lower precision data type. And what quantization allows us to do in the context of things like language models is take these really large language models like this one with many billions of parameters and trim them down into more workable formats so that it's better to actually be able to run on more consumer hardware. Not everybody has the infrastructure or things like the GPU clusters needed to load and run these models at their full capacity. So usually this transformation is done to allow it to run with less VRAM or less memory on easier to access or cheaper hardware, or even things like CPUs. And it's how popular programs like Ollama or LM Studio are actually able to convert and run new and latest large language models on consumer grade hardware. So we can see with this example of Llama 3.2 from Ollama, they have quantized it down using Q4KM, which we'll get into a little bit later. And so to understand what quantization is doing here, we need to take a look at how the actual internal weights of language models are stored. Taking a look at this Llama 3.2 1B model that I fine-tuned a few weeks ago, if we take a look at the actual internal layers of it here, which will be right above my head, we can see that each one of these layers within the model itself are in this precision here, and the precision says F16, which stands for floating point 16 precision. Digging one level down, if we actually open up one of these tensors in one of the models, we can see here now that the weights are stored in something that looks like this. All of these specific numbers in these large arrays of size 2048 by 2048. But actually printing out these original weights in this tensor here into these numbers is not the way that they're literally stored or loaded onto things like our GPU VRAM or in a file. Instead, these numbers internally are stored as binary representations. And so while computers work better with binary, we humans usually use the decimal numeral system, otherwise known as the base 10 positional numeral system. Which what that means is if we have a number like 254, we can look at the different positions of these numbers here and represent this differently. So it would actually be 4 times 10 to the power of 0 for the 0th position, or the first starting position, which would then be, of course, equal to 4 times 1, which would be 4. And then looking at 5, which is in the second or first position starting from 0, that would be 5 times 10 to the first, or 5 times 10, which is 50, and then so on for 2, which is in the second position, which would turn out to 2 times 100, and then adding up all of these, we get 254. But working with decimals is a little bit more complicated with computers because computers tend to like things that are very binary or either true or false. In most cases, a lot of computer hardware reads signals as either on or off, which is best represented as 0 or 1. Thus, being able to represent numbers as bits or binary digits became popular in modern computing. And binary is then, instead of being a base 10 numeral system is a base 2 numeral system because we only have 0 or 1. So if we look at a binary number 11111110 that has 8 positions, we can do a little bit of the same thing that we did with the decimals, of actually taking a look at the first position here and saying that it's 2 to the 0 times 0, and then 2 to the 1 times 1, which, starting to get this out, 2 to the 2 times 1 will look a little bit exponential. And then if we add all of these up, you'll see that this becomes our original number 254 that we just looked at, but now it is in a binary form with this base 2 system. And this can also handle fractions too, where everything past the 0 on the right is increasingly going to negative powers from -1 up to -infinity. I'll spare you from me writing out the full math this time, but looking at this example, if we see 101.11, we can see that we do the original binary conversion for the first 3 numbers, and then the last 2 here are going to be going under -1, and then 2 to the power of -2, which comes out to 0.75. So this number then becomes 5.75, but in binary form with decimals. Decimals in this case being the fractions. But the raw numbers that make up the weights of our language model aren't stored in actual binary just as the number themselves. They are stored with some sort of precision, which in this case is actually talking about floating point numbers, which can essentially be thought of as the scientific notation of binary. But instead of using powers of 10, which we do in scientific notation, we instead use powers of 2 because, of course, instead of working with decimals, we're working with binary. Floating points came around because of a need of being able to efficiently represent numbers in a small amount of bits for computer computations. Essentially, it's a way of being able to represent pretty much most of the numbers that most computations and things in the world fall into in just 32 bits. And so the actual numbers within deep learning models' weights are stored using these floating points, which take on and look a little bit something like this. The most common and standard is IEEE 754 single precision 32-bit float, which is a bit of a mouthful, but essentially it is looking at this binary of 32 bits, where the first one is the sign, followed by 8 bits for the exponent, and then 23 bits to represent the fraction, which this part is also sometimes known as the mantissa or significand. The formula for converting from the binary floating point back and forth to a actual decimal number then looks a little bit something like this, which is a little bit easier to understand once we go and look at actually converting a number. So taking a look back at our number and example of 5.75, we first have to, of course, convert this into binary, which we already did this a little bit ago and found that it was 101.11. That is then normalized into 1.0111 times 2 to the power of 2, which is very similar to our base 10 scientific notation. Splitting this number into its 3 parts, we see that it is a positive number, so we have a sign of 0 because 0 is going to represent positive, and 1 is going to represent negative for the first one here. We have an exponent of 2, which is this 2 raised to the 2, and then our mantissa or significand, which is the full number right now, is 1.0111. What we then is actually add a bias to our exponent of 2 of 127, so it becomes 129. The reason for this is because in the 8 bits here, we can represent numbers from 0 up to 255. However, we want to be able to represent both large positive numbers and then also fractions of numbers. So this is offset with 127 to be able to get both the largest positive numbers that we can get, as well as the more precise fractions. So our exponent then is going to have to become 129, and converting that into binary becomes 100000001. And so now we have this plus a 0 on top of that, which makes up our first sign and exponent. And so now that we have the actual sign and the exponent coming from our number of 1.0111 base 2 times 2 to the 2, all we need to do now is deal with this. and that becomes our significand. So we always assume and will always have a leading 1, which means that what we're going to do is just take everything after the actual point, and that becomes our significand here. So it's 0, 1, 1, 1, and then because it doesn't fill the remaining bits, we add in a bunch of zeros to pad it, which gives us our full 3 parts of the sign, the exponent, and the significand. And so putting them all together into floating point 32 single precision format looks something like this. And so essentially, this gives us a way to convert most numbers that are needed for most calculations into 32 bits, which comes out to 4 bytes per number. But then tying it back, once we have many billions of numbers to actually store, this can add up to a lot of gigabytes of data. So you can see in my model that we're not actually storing 32-bit precision. Everything is stored in 16-bit floats, or what is otherwise known as half precision, which has a single bit for the sign, 5 bits for the exponent, and then 10 bits for the significand compared to the 32 bits. But then also in deep learning, we see another common type of BF16, which stands for brain float 16, and is 1 bit for the sign, 8 for the exponent, and then 7 for the significand. So these precisions of 32-bit and 16-bit, or BF16, are the 3 main data types that most language models or deep neural networks are going to be stored or trained in. And these precisions are needed with these models to actually be able to capture all of the different nuances and little bits of information that are captured during the training of these things. But of course, as a result, storing all of these numbers in these high precision formats takes up a lot of space and is very difficult to run on something like a MacBook or a consumer grade GPU. And as it turns out, we don't actually need this full precision when running all of our inference through these models, or maybe using a language model to generate text, to be able to get a same quality output. And so researchers realize that what they can do is actually do this conversion process of converting from full or half or BF16 precision down to much more compressed versions of the numbers, like 8-bit or even 4-bit, and maintain still most of the actual performance of the models while being able to drastically reduce the size and computation needed. And so that's where quantization actually starts to come into play with things like language models, where these researchers were able to figure out that they could map essentially the floating point 16 or half precision vectors and tensors down into int8 vectors, which cover the range of -127 to 127. So you might be wondering, how can I take something like half precision, which covers such a large range of numbers, and squeeze it down into only 255 values? Wouldn't that be a very lossy compression, where we're getting rid of a lot of the little nuances that we're able to capture in these more precise numbers? And you might think yes, but as it turns out, it's actually not too bad if you're going from something like floating point 16 down to an 8-bit representation. And this is because the actual weights themselves, the specific numbers when we're running the inference or doing the generation with a language model, don't actually matter all too much. Instead, the actual relationship, or kind of the differences between the values between all of the weights, matter more than the literal numbers of each individual one. So if we're able to algorithmically and efficiently map these numbers down into these smaller, more easy to represent and store values, we can maintain most of the same performance, but actually compress the model's size and footprint a lot. So much so that we can see the experiments ran here found very little differences between the FP16 and the int8 quantized versions of these models. It was even found that we can quantize down to 4 bits, or just 16 different numerical representations for every single number in these weights, and still get very, very decent performance. And even more aggressive, we're starting to look into 1-bit quantization. I'll leave these resources down below if you're interested in more of the specifics of the math and the algorithms that go into the actual conversion and quantization of these weights down into it. But the good thing is that there are a lot of existing packages that can actually do this quantization automatically for us. So let's take a look more specifically at actually using these and comparing our models. So hopping over to the code, we'll be loading my 1 billion parameter Llama 3.2 model here and taking a little bit of a look under the hood. But the first thing that I want to show is how you can actually use the bits and bytes package that comes in Transformers to load and do these quantizations. And it's super easy. When you're actually loading just the base model, most of the time in Transformers, you're going to be using some sort of auto model for causal LM from pre-trained and then passing in a model ID, which is the Hugging Face repo here. But what you can also do is pass in a quantization config. And so this is where we're going to have the bits and bytes config. To load it in 8-bit, all I need to do is create this config that has load in 8-bit equal to true, and then pass it through into our quantization config. The same is true for 4-bit. I added a few different arguments here that all come from the blog post that I'll have linked in the description that introduces the 4-bit method. But right off the bat, after loading it, we can see that the base model takes up about 4.9 billion bytes, the int8 model takes up about 1.5 billion bytes, and the 4-bit model takes up about 1 billion bytes, which corresponds to about 4.9 gigabytes, 1.5 gigabytes, and 1 gigabyte to load. So already we can see that we were able to reduce the footprint of actually storing this model to about 30% of its original size with 8-bit quantization, and then about 20% of the size with 4-bit quantization. Running through the actual VRAM requirements, it takes about 5 gigabytes of VRAM to load this base 1 billion parameter model, but then only 1.7 gigabytes with the 8-bit and 1.2 with the 4-bit. So already you can see that this is a drastic decrease in the actual resource requirements for running these models, with consumer hardware generally having around 12 or at the high end 24 gigabytes of VRAM for your GPU. Being able to reduce down the requirements by 80% is incredible gains if we're able to manage the same actual performance. And so actually opening the model up and taking a look at the numbers like we did earlier in the video, we can see how these quantizations have actually transformed them. We have, of course, our original weights that we saw originally, which are in floating point 16 half precision. And then now in our 8-bit weights, we can see that they are whole numbers and should be within the range of -127 to 127. The 4-bit weights did something a little bit more specific. They're actually an unsigned int8 data type here, which is why it looks like just whole numbers of the int8 variety, but essentially these are going to be split up into 2, and each one of those become the 4-bit weights. It's just one extra little step that the people who implemented this added in for an extra efficiency. So we can say with confidence that our quantization down into these 2 different types worked effectively. But quantization is only as good as actually being able to test out the capabilities of the model. So let's actually generate a little bit of text with each one of these and see what it responds with. And so our big prompt is going to be, what is a language model? And we're going to run it through all 3 versions of the model. Now, keep in mind that this is still a 1 billion parameter model, so it's not going to be as robust as the larger models like the 70 billion parameter ones, but we should still be able to see a difference. And so now we have all 3 texts generated from our what is a language model prompt side by side. And the cool thing here is that we can see that the base model said it's a mathematical model that can generate text. It's used on various applications such as NLP, machine translation, and speech recognition. But then going down to our 8-bit quantized model, it also says it's a mathematical function that maps inputs to text, used in natural language processing, translation. It also goes on a little bit further to talk about how it's trained on a large corpus of text. And then our 4-bit model had a very similar and also equally, if not even more, lengthy response here. So just holistically looking at this and assessing these responses, it's cool to see that despite this massive compression of the model, we're still able to get text that is very good output from it and almost indistinguishable from our base models. We can also look at a common measurement called perplexity that actually measures how well the model is predicting the next token that it generated here. And essentially what it's going to tell us is whether or not the model is actually very confident or uncertain in its predictions. This is, of course, done by looking at the outputs and calculating a little bit of the loss between the actual outputs here and what it kind of expects to be generating itself. And so looking at these perplexity scores from our base up through our 8-bit and 4-bit, we see that the base model had a perplexity score of about 3.04, and then our 8-bit had one of 3.48, and 4-bit respectively had 3.46. So it is a little less certain on actually generating this type of text, but not so much so less certain than the actual base model is. So we can accurately claim that there was a slight degradation in the model's performance when doing this quantization. However, it is very much still similar to the levels that our base model is at, which is phenomenal to see because we've essentially have a model that is 20% the size of and 20% the actual resource requirement of our base model that is only slightly worse than the base model. So this shows a lot of promise for actually being able to compress down these massive models into more accessible formats that can be run on limited hardware. And so past a little bit of this more basic quantization, I would be remiss if I didn't bring up the quantization and conversion of the GGUF format, which GGUF is actually a format developed by Georgy Kurganov, who is the developer of Llama CPP or Llama C++, which is pretty much a framework for efficiently loading and running language models on pretty much any piece of hardware you want that supports the C language. It's a format that's been designed to both efficiently store and serve language models in a single file, which is really cool when you take a look at GGUF repos, and all they have are just single GGUF files. And as we mentioned in the beginning, it's also a very popular format for things like LM Studio or Ollama, where we can effectively run these models on consumer-grade hardware in these quantized formats on things like CPUs with very limited actual resource needs. And so Georgy's Llama CPP library here actually includes everything you need to do the quantization and conversion of models into this format yourself. On top of combining everything into one model, they also have a bunch of different quantization methods, which can go all the way from 8-bit quantization down to 2-bit quantization, with various different combinations of things for various different layers. One of the more popular ones is this Q4KM, which uses 6-bit quantization for half of the attention and feed forwards. The rest is 4-bit kquants quantization. To actually quantize a model into this format, we'll first install and clone the Llama C++ repo, make everything there so that we've got all the nice files, and then what we can do is download our model. So that is going to download straight from Hugging Face real quick. And then once that's done, we can use their script convert HF to GGUF, and that will do the first conversion from the Hugging Face format, which is just a safe tensors file, into the GGUF file in float 16 half precision. And so that takes absolutely no time at all. And then once we're in our GGUF file, all we need to do is run through our quantization method, which we'll be using the Q4KM method. And so running that then will also not take too long. We can see that it's started already and is almost about a third done. And in no time at all, we have quantized down our model into this new format. So now what we can do is try it out by loading up the terminal here and pasting in this line. And we can now ask it, why is the sky blue? And you can see that our model is working nicely in this format, quantized down to 4-bit. And so now this is actually even less of a footprint than our prior model. It is only going to be about 800 megabytes. And also as a plus, doesn't require any GPU resources to run. We're loading this straight onto our system RAM, which is not even taking up all too much here, and we're still able to get good performance. If you're interested in trying this model out yourself, I've got it uploaded here onto Hugging Face as well. But with that being said, quantization is really an important subject to understand if you're trying to optimize the actual running of, loading, and storing of language models onto any sort of consumer-grade hardware. It's a super powerful technique being used to balance both the performance and the efficiency of language models, and being able to more widely be able to use them without needing super expensive storage requirements or VRAM requirements. So, hope you learned something interesting today about quantization. If you liked the video, like the video. If you've got any questions, ask them in the comments below. And if you want to see more like this and support the channel, consider subscribing. Thank you and have a great day.